Hey, Math 30-1 students, welcome back. Let's take a look at Lesson 7 in Perms and Comms, Pascal's triangle. We're going to do, first of all, investigate kind of where Pascal's triangle comes from by looking at how we would expand a binomial. So let's say we had something like x plus y to the 0 exponent. Now, if you recall, anything to the 0 exponent is going to be just equal to 1. Okay, now let's look at x plus y to the 1. Well, if the exponent's just 1 on that, that's going to be equal to x plus y. Now, a little bit tougher, x plus y squared, as you recall, would be the same as writing x plus y times x plus y. Okay, you don't just square each term individually. Then we have to expand this using distributive property or FOIL. And so we multiply the first terms together, x squared, outside, inside would add up to 2xy, xy plus xy, plus the last terms together, y squared. And there we go, that's expanding x plus y squared. If we're to do x plus y cubed, we would have to go x plus y times x plus y times x plus y. Now we've already done the work for two of those multiplies together, so I'm just going to copy that down from above. And then that means we only have to multiply this binomial by this trinomial, which is a bit of work, but basically this x has to be multiplied to each term inside, and then the y will have to be multiplied by each term inside. Okay, sort of like FOIL, but a little more complicated. Okay, so let's do that. X cubed plus 2x squared y plus xy squared. And notice you could write that as y squared x, but you usually write it alphabetically, so that's why I put the x first for that term. Okay, now y gets multiplied by each of those. X squared y plus 2x y squared plus y cubed. And now we collect like terms, and we would have, let's see, is there any other 2x squared y's? Yes, there is, that one and that one. So add the coefficients, 3x squared y plus xy squared, 2xy squared plus 3xy squared plus y cubed. Okay, now you can imagine now how much work x plus y to the 4 is going to be, because we'd have to take these four terms that we have and multiply each by x and by y. So you can go ahead and do that if you like, and then we're going to copy our answers down below here. So you can pause your video and go ahead and do that. Okay, how did that go? Whew, that was a lot of work, wasn't it? Okay, so check and make sure you got the same answer that I did when you expanded that. And then when you copied your answers down below, we should have this. They provided like the first term for you for each one. So now we're going to analyze this. The good news is we're looking for a shortcut to do this. And this is kind of what Pascal would have gone through to discover his triangle. But state the number of terms in the expansion of x plus y squared. So that's this one here. We have 1, 2, 3 terms. Okay, so that one had 3 terms. Okay, state the number of terms in the expansion of x plus y cubed. Okay, well that would be 4 terms, right? So we're looking at this up here, 1, 2, 3, 4 terms. Okay, terms are separated by plus or minus signs, right? Okay, and x plus y to the 4, 1, 2, 3, 4, 5. Okay, now you're probably starting to see a pattern here, right? Compared to the exponent, right? When the exponent was a 2, there were 3 terms. When the exponent was a 3, there were 4 terms. So what would you guess if our exponent was 20? How many terms would we have? Yep, you got it, 21 terms. So in other words, the number of terms is 1 more than the exponent. Okay, now part E, state the sum of the exponents in each term in the expansion of x plus y squared. So what they're talking about there is if we go back up and look at each of these. So let's say we pick, well, we can look at x plus y squared. So the exponent here is a 2. Here 1 plus 1 would equal 2, and here again it's a 2. So the sum of the exponents is going to be 2. X plus y cubed. Okay, so we have a 3. We have a 2 plus 1, which is 3. We have a 1 plus 2, which is 3, and then a 3 again. So in other words, excuse me, the sum of the exponents adds up to 3. Okay, you see a pattern here? Okay, x plus y to the 4, we would expect that the sum of the exponents would be 4. 4, 3 plus 1, that's 4. 2 plus 2, that's 4. 1 plus 3, 4, and 4. All right, we've got the pattern. It looks like the sum of the exponents in each term is the same as the original exponent on the binomial. So in other words, we would expect the sum of the exponents for this last one to be, yep, you got it, 20. Good. Okay, complete the following arrays which show the coefficients of the terms in each of the expansions. Okay, so what we're doing now, I'll use a different color for this, is we're going back up to our expansion and we're looking at, see the example they gave you here for x plus y squared. We're looking at the coefficients, the numbers in front. Now there's no number in front of this, but I could write a 1 in front of the x squared and the y squared. So the coefficients would be 1, 2, and 1, and that's what they've copied down here. So let's do, it might be easier to do the next one, x plus y cubed. So we have a 1, a 3, and a 1. So we copy that down here, 1, 3, 3, 1. All right, you guys go ahead and finish up the array for that here, and then you can copy it again over into this triangular array. Okay, so pause your video. Okay, so we should have arrived at the triangular array, or the array of 1. Really, this value was only 1. The coefficients of x plus y, 1 and 1, etc., etc. Okay, now we're leading into what's called Pascal's triangle here. So notice it's set up like a triangle. Okay, explore the patterns in the triangular array and complete the next row. Okay, so in this triangle here, do you see any patterns on, well, first of all, I would notice that there are 1s running down the outside of this. So the next row would probably have a 1 at either end, and it looks like the number of terms in each row keeps increasing by 1. So I would expect that we would have 1, 2, 3, 4, 5, so 6 terms in the next row. And I don't know if you've discovered this yet, but if you add the two above numbers, you get the number below. 1 plus 1 is 2. 2 plus 1 is 3. And again here, 2 plus 1 is 3. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Okay, so let's put that to work to do the next row. We have a 1 on the outside. A 1 plus 4 is 5. A 4 plus 6 is 10. 6 plus 4, 10. 4 plus 1, 5. And then again, we have an outside number 1. Make sure we have one more term. So we had 5 terms in the last row. 1, 2, 3, 4, 5, 6. We have 6 terms. Good. If you guys want to try and do the next row, pause your video, and then I will complete that for you. You can check it. Okay, so that next row would have been 1, 6, 15, 20, 15, 6, and 1. Hopefully you got that as well. Okay, let's look at the next page. So here's where they summarize what we discovered on the previous page. They've kind of collected all the expansions together here. But what we noticed was when the exponent was, say, a 4, we had how many terms? 1, 2, 3, 4, 5. So in other words, if our exponent was n, generally speaking, then we would have n plus 1 terms. The sum of the exponents of x and y in each term, so if the exponent was a 5, 3 plus 2, 2 plus 3, 1 plus 4, always adds up to this number. So the sum is n, generally speaking. Okay, exponents on x, it looks like the exponents on x start at whatever the n value is, and then they decrease until pretty much they're down to 0. So the exponents of x decrease by 1, I'm going to say, term by term from n to 0. And then if you look at the exponents on y, they start off as 0, y to the 0, y to the 1, 2, 3, 4, and they reach, again, the n value. So they increase by 1. Okay, now the coefficients. So if we look at the coefficients, which really was Pascal's triangle, right? What they're looking for here is they form a symmetrical arrangement. Notice how if I wrote 1, 4, 6, I would expect the next two to come back down again, 4, 1. That's what it's sort of symmetrical about the middle there. So we're looking for the word symmetrical there. Good. All right. So if we put those coefficients in a triangle like we did on the previous page, we have what's called Pascal's triangle, named after this guy Pascal, who, I don't know, had time on his hands. I don't know how he came up with this, who developed applications of the triangle in the 17th century. So they have you completing the next 3 rows. We did that on the previous page, so I think that we're not going to do that yet. And these expansions we'll maybe get to on a previous one. But so we'll come back to how to do that, okay? Which row of Pascal's triangle is equivalent to the coefficients of the terms in the expansion? So in this would be called row 1, right? And this would be called, and that would be for x plus y to the 0. Next one, x plus y to the 1, but it's row 2. So notice the exponent, the row is basically one more than the exponent, right? So if we look at an exponent of 6, that would correspond to row 7. And for the exponent of 7, that would be row 8, etc. So in other words, this last one where the exponent's just n, it would be row n plus 1. Okay? All right, let's look at the next page. Okay, so you're probably wondering why this topic, because it's pretty different from what we've been doing, is even in this unit. Well, the really cool thing is these numbers in Pascal's triangle are actually combinations. They're the same as n choose r, which I think is really cool that that pattern would develop. So 1, for instance, is the same as 0 choose 0. So, and then in the next row, 1 and 1 is 1 choose 0, 1 choose 1. Let's say we take this row here. 1 is equivalent to 3 choose 0. 3 is equivalent to 3 choose 1. And 3 again is equivalent to 3 choose 2. And then finally 1 is equivalent to 3 choose 3. How cool is that, that these are actually combinations? And can you see the pattern developing here? With the 3 stays the same as your initial, and then 0, 1, 2, 3. Okay, so again, cool. State the first 3 terms of the 8th row of Pascal's triangle in numerical form and in combination form. So we're talking about the 8th row. Okay, so the first 3 terms, we know the first one's always 1, and then we add, so 7, and then add again. 6 plus 15 is 21. So the first 3 terms would be 1, 7, and 21 in Pascal's triangle. As a combination, if you look at the pattern here, 6 was for row 7 here. We're in row 8, so it's going to be 7 choose, and it starts at 0. Then 7 choose, and it increases, so 7 choose 1, and the next term would be 7 choose 2. All right, now then it asks you to state the last 3 terms in the 8th row. So we're looking at basically these terms, but for the next row. Okay, so again, it should be, I'm going to start at the end here, so it'd be 7 choose 7 should be the last term, right? And then the one before that should be 7 choose 6, and the one before that would be 7 choose 5. Okay, does that make sense? Oh, and numerical form, it would have to be, well, it'd be the same as the first 3 terms, wouldn't it? 1, 7, 21. Now, I just want to mention something here that's really cool. In combinations, we talked about how, so we just discovered that this is equal to this, right? 6 equals 6, right? Remember how we talked about if the k values added up to the n value in n choose k or n choose r here, that they were equivalent. 6 choose 1 is equivalent to 6 choose 5. 1 plus 5 is equal to 6, and that's why they're equivalent. Same thing here. 2 plus 4 is 6, so these two would equal each other as well. Okay, another cool connection. Okay, use Pascal's triangle to write the following as a single combination. Okay, so 4 choose 2 plus 4 choose 3. Okay, so 4 choose 2 plus 4 choose 3. We're looking at this, and those two added together we know is equal to 5 choose 3. We're totally using Pascal's triangle here. Okay, not so much figuring this out with combinations, but 6 choose 0 plus 6 choose 1. So 6 choose 0 plus 6 choose 1 should give us this term, which would be 7, choose, and that would have to be the next, not the first one, but the second one, so 7, choose 1. Good, time's up. See you in part 2.